as yet another testament to my cheapness, I'm going to slide a slightly used piece of paper to cover up dipole-dipole forces as we look at a subcategory, some might say, of dipole-dipole forces, and that is hydrogen bonding. So I'm going to call this 2. Even though I never write 2 in class, that's what I'll write right now. Hydrogen bonding. Sorry, my dog was crunching up his lunch next to me, dinner, I guess. Anyway, hydrogen bonding, which has been redefined in the not-so-distant past as weak covalent bonding. All right, and if you think about what we wrote in here, we're saying it's a dipole-dipole force that is stronger than regular dipole-dipole forces, but we're not actually getting a bond. So I realize there's some ambiguity there if we're going to define it as weak covalent bonding. The key part here is that it has certain elements that must be present. So it's weak covalent bonding between or among slightly positive hydrogens, all right, and slightly negative nitrogens, oxygens, or fluorines. All right, and what you can see there is something we had discussed previously, and that is the idea that higher electronegativity differences make things more ionic, or in this case, stronger dipole-dipole force. So the question often comes up, if we look at these electronegativities, hydrogen's a 2.1, nitrogen's a 3.0, oxygen's a 3.5, excuse me, and fluorine's a 4.0. So what we have here are stronger dipoles. Looking at a simple example, or perhaps the simplest example, HF, we can see how this works out. Again, there's only two atoms present here, so we don't need to worry about drawing a separate three-dimensional structure. I'll draw the hydrogen, and I'll draw the fluorine with our dots on there. When we look at the electronegativities, I had written it up there, but it won't hurt to mention it again. Hydrogen has an electronegativity of 2.1, and fluorine is a 4.0. So we have a difference there of 1.9, which you would almost think borders into ionic territory, but this is a covalent bond. It just happens to have a very strong dipole in one direction. So this fluorine is going to end up slightly negative, and the hydrogen is going to end up slightly positive. Now, at a glance, this is dipole-dipole when we put another HF there. In fact, let's do that. We've got our slightly positive hydrogen, slightly negative fluorine. We have an attraction among opposing dipoles right there. It just happens to be a stronger attraction due to the larger electronegativity difference than we see with the other things. And so we get slightly higher boiling points, melting points, things like that, lower vapor pressures, and we'll see how that works in a bit. So again, at a glance, it looks pretty much the same as our regular old dipole-dipole forces, but the key factor here, we've got a slightly positive hydrogen attached to a slightly negative nitrogen, oxygen, or fluorine. So just toss one more on here. Sorry, slightly negative, slightly positive. And in the same way as you could note that there are potential repulsions between the fluorines or whatever, but that just ends up making things align a certain way. Once again, this highlighted stuff here is an attraction, right? Specifically, it is hydrogen bonding. I think it's worth our time right now to take a look at a classic hydrogen bonding versus regular old dipole-dipole forces example, and that involves H2S, hydrogen sulfide gas, and water, H2O. So a common type of question that comes up is like, explain why the boiling point, temperature BP, boiling point of H2S is so much lower than the boiling point of H2O. All right. Classic question, as I said, and if we're looking at physical properties like boiling point, then the first place we want to start our investigation is looking at intermolecular forces. All right. Valence electrons, again, we used as a way to predict in general chemical properties. Physical properties, we're very often going to look at intermolecular forces. So let's draw them out. We're going to need to see the 3D structure for these, which coincidentally will step on our Lewis structure and make it happen. But so as we begin our justification or our explanation, we'll draw out these Lewis structures, H2S. We've got sulfur with non-bonding pairs. We're going to attach those hydrogens, and it has the exact same three-dimensional molecular geometry as H2O. In fact, oxygen's in group 16, sulfur's in group 16. We would expect very similar things going on. Now, I drew this as an approximation of our tetrahedral-based bent structure for 3D. So these aren't just Lewis structures. Our bond angle here, we would expect less than 109.5. There is a larger than I would expect bond angle between those two things. But if we're just talking about molecular geometry, both of these things are tetrahedral-based bent. And they both have net dipole towards the higher electronegativity atom. In this case, the H2S has a dipole towards that sulfur, and in this one, the H2O has a net dipole towards that oxygen. I'm going to cheat and draw it in much larger, because I never wrote H2O over here. Looking at our electronegativities, H2S 2.1 versus 2.5, and 2.1 versus 3.5. So pretty significant difference in electronegativity for those things. So we have this information. In fact, I'll give you the exact numbers. Our boiling point for H2S is negative 60 degrees Celsius versus our boiling point for H2O, which is 100 degrees Celsius. So as we look at those numbers, it's a pretty huge disparity. When we make some predictions about the intermolecular forces that are present, and I'll cheat by pointing in two places, we want to look at this ranking right here. The farthest left is the one that matters. Is it ionic? No, we don't have an ionic species. Does it have a net dipole? Yes, both of these are tetrahedral-based bent, and they have a net dipole towards the higher electronegativity atom. And do we have hydrogen bonding? So that's the next question we're asking. In this particular case, we have hydrogen and sulfur, and for us to have hydrogen bonding, we need that slightly positive hydrogen attached to a nitrogen, an oxygen, or a fluorine. So we don't have hydrogen bonding there. We do have hydrogen bonding there, which is stronger, and then we would expect that stronger attraction to make it harder to get the particles far apart. It would take more energy to boil it. Okay, so let's write that out. And they both also have London dispersion forces. And I do want to put those because they're kind of an interesting topic in the big picture. So they both are bent, tetrahedral based. They both have a net dipole. The H2S has dipole forces and London dispersion forces, whereas the H2O has hydrogen bonding and London dispersion forces. All right, we're not worried about the London dispersion forces if we have those other things. Hydrogen bonding is stronger than dipole-dipole, and that's what our explanation will be. The hydrogen bonding is stronger than regular dipole-dipole. And I'm going to write in these next words, so the particles are more strongly attracted, and then there's a higher boiling point, more energy required to get them apart. So hydrogen bonding is stronger than regular dipole-dipole forces, therefore there's a stronger attraction, right? And more energy is required to separate them. Which is resulting in a higher boiling point. All right, so if we just glance at the pictures once again, The molecular geometry, same thing, both polar, but the hydrogen bonding is a stronger force, and it's going to take more energy to get the particles farther apart.